This is a Rubik's Cube, and this is a puzzle I got in Japan. Solving a Rubik's Cube requires rotating each of the faces until all sides show the same color. This puzzle requires rotating the two inner pieces in a certain way so that they can be separated from the outer chamber. Both of these have an infinite number of solutions. So what's the difference? When solving a Rubik's Cube, every move we make results in a distinct configuration. So even if it takes 100 moves, or 1,000 moves, or if you're just spinning one side over and over until the end of time, the configuration after each individual spin is still distinct. So if we add up all the different ways to solve a Rubik's Cube, the number of solutions is infinite, but it's still countable. And because it's countable, we can model it using a discrete random variable. What if we wanted to model the number of moves in the infinity puzzle? Does that even make sense? So what would be counted as a move? In the case of a Rubik's Cube, we counted a 90-degree turn as a distinct move, and so we could count the number of moves. Solving the infinity puzzle, though, requires a series of twists and turns. So I could rotate an inside piece 30 degrees, or I could rotate it 29, or I can rotate it any number in between. And that's why this puzzle has an uncountably infinite number of solutions. When we talk about events that are uncountable, we use the continuous random variable. So because the support of a continuous random variable is uncountably infinite, the probability associated with any one point value is always 0%. With continuous random variables, we always work with intervals. So if you've heard that calculus is needed for Exam P, this is where a calculus comes in, for continuous random variables. We're not going to go into a full review of calculus in this video. The main thing to know is that an integral is a way to sum an uncountable number of outcomes. So from the discrete case, whereas we used to use sums, we now use integrals. And these formulas are going to look very familiar if you already understand discrete random variables. Just like with discrete random variables, there's also a probability function for continuous random variables. In this case, we call it the probability density function, or PDF. The PDF is denoted by f of x, and because a continuous random variable takes on 0 probability at any point value, when we talk about probabilities of the PDF, we define intervals. So the probability that x is between a and b is given by the integral from a to b of f of x dx, where f of x is your probability density function. And this function can be represented by a variety of mathematical functions. Similar to the PMF for discrete random variables, the PDF for continuous random variables must also satisfy two conditions. The first condition is that the PDF is greater than 0 for all values of x, and the second is that the integral of f of x totals 1 for all values of x. So when you integrate from negative infinity to infinity, that gets you a value of 1. And that's just saying the total sum of all probabilities is equal to 1. Continuous random variables also have a cumulative distribution function, which is similar to the cumulative distribution function for discrete random variables. And it gives the probability that your random variable x takes on a value less than or equal to a specified value. In the discrete case for a CDF, we took the sum of all values less than or equal to that specified value. In the continuous case, again, we can't use summations because there is no probability associated with each point value. So instead, we take the integral from negative infinity to that specified value of our PDF, f of x dx, or in this case, f of t dt, since we're using x as that specified value. The CDF also has 3 properties that it must satisfy. These aren't really going to show up directly on the exam, but if you're calculating a CDF and it seems like your CDF is violating one of these properties, then that should be an alarm that something's off. The first property is that the CDF is a non-decreasing function of x. So as x increases, the CDF must also stay the same or increase. And that makes sense from the definition because we're taking the integral from negative infinity to x. So if x gets higher, the range of our integral also increases. The second property is that the CDF starts at 0 and ends at 1, which makes sense because the probability is accumulating as x goes to infinity. The third condition is that the CDF is right continuous, which effectively means that there are no jumps as x approaches infinity. It's a little more nuanced than that, but that's a bit outside the scope of this video. The expected value is your average, so your expected outcome over a large number of trials. And the formula to calculate it is the integral across all values, so from negative infinity to infinity of x times f of x dx. The nth raw moment is the expectation of x raised to n. This is most commonly used when calculating the variance, which we'll see later in this video. The formula to calculate the nth raw moment is the integral from negative infinity to infinity of x raised to the n times f of x dx. The variance is a measure of dispersion from the mean. It's also known as a second central moment, and you can see that from the formula. The formula for the variance is the integral across all values of your square deviation from the mean, which is x minus e of x. Typically, when solving questions, there's a shortcut formula to use to calculate the variance, which we'll talk about later in this video, but this definition here is a bit more intuitive. So the variance measures the spread of your distribution. A lower variance means that the probability is concentrated more around the mean, and a higher variance means that the values are concentrated less around the mean. The standard deviation is also a measure of dispersion. Usually when calculating the standard deviation, you'll need to calculate the variance first and then just take the square root of that, and that'll get you to the standard deviation. The standard deviation is sometimes preferred over the variance. The variance is expressed in terms of x squared. For example, if you have a distribution on the height of people, the variance is actually the height squared, which doesn't really make that much sense. So to get back to a unit that's comparable to height, you take the square root of the variance to get the standard deviation. When solving questions, you'll need to know the various mathematical rules around expectations and variance. The expectation of a constant is just that constant, and the variance is 0 since there's no randomness involved. For the expectation of a constant times x, the constant can be distributed out. So e of c times x equals c times e of x. This next one you have to be a little bit careful with. The variance of c times x is c squared times variance of x. The expectation of an arbitrary function, say g of x, is the integral from negative infinity to infinity of g of x times f of x dx. Earlier in the video, we saw multiple applications of this with the expected value, moments, and variance. When solving for the variance, similar to the discrete case, there's a shortcut formula where the variance of x equals the second raw moment minus the expected value squared. In most cases, when calculating the variance, this is going to be the more efficient formula to use. So you'll need to calculate the expected value and the second raw moment to get the variance. The other rules in this visual all include more than one variable, so multivariate random variables, which we'll cover in a later video. A percentile is a value of x, so a value on your support, such that p% of other values are less than the percentile. Here we use a notation capital P of lowercase p to represent the percentile. Sometimes you'll just see capital P or pi of p. Regardless of the notation, the definition is still the same. So up until now, the PDF has sort of been more useful than the CDF. This is a case where you can directly use the CDF to calculate a statistic. The median is a special case of a percentile that splits your distribution in half. So it's the 50th percentile. In terms of formulas, we can substitute 50% into the percentile formulas to solve for the median. Just like with discrete distributions, there are specific continuous distributions tested on the exam. In this video, we'll cover the continuous uniform, the normal, and the exponential distributions. Gamma, log normal, and beta are also listed on the syllabus, but the chance that they'll appear on the actual exam is relatively low. So I would prioritize those distributions as one of the last things to study. If you want more information on any specific distribution or anything we've covered in this video so far, there's a written course on the Actuarial Nexus. I'll leave a link in the description below. The continuous uniform distribution assigns equal probability to all values of x within a given interval. The continuous uniform distribution is very similar to the discrete uniform distribution. The continuous uniform distribution has a support that has an uncountable number of values, and that's what makes it continuous. Similar to the discrete uniform distribution, the continuous uniform distribution also takes on two parameters, a minimum value and a maximum value. When we look at the PDF of a continuous uniform distribution, the support runs from A to B. And since the probability of any value within that range is the same, the density function can be graphed by a straight horizontal line. And because a properly defined PDF must integrate to 1, we can view this as a rectangle with area 1. And so if the width is b minus a, then the height must be 1 over b minus a. And so the PDF is 1 over b minus a. We can then apply the formulas we covered earlier in this video to calculate the CDF, the expected value, the second moment, the variance, and the standard deviation. If you do that, you'll get the results that you see on screen here. Is it easy? Relative to the other continuous distributions, this is probably the easiest one, but overall the continuous distributions are probably going to be more challenging than the discrete distributions just because you're working with calculus. Will it be tested? This gets a 3 out of 5. There are a good number of SOA sample questions on it, so there's a good chance that this could appear on the exam, and it can also overlap with concepts in the next video such as deductibles and policy limits. The exponential distribution models the time between events where the rate of the occurrence of the event is constant over time. So the rate of occurrence, lambda, is the inverse of the mean, 1 over lambda. So for example, if the time between claims follows an exponential distribution and we define lambda as 2 claims per hour, then using the definition for the expected value of an exponential distribution, we get that the average time between claims is 1 over 2 2 or every half hour. Now this is just on average. It doesn't explain the distribution between claims, so it's not like every half hour there's a claim. When we look at the PDF of an exponential distribution, you can see that the PDF decreases over time. And so a relatively high amount of probability is associated with the time intervals that are shorter. So in the example from earlier, you can have a claim that comes in 20 minutes, then another one in 30, then another one in 25 and 15 and so on. But you can also have a claim that comes in 40 minutes or an hour or 2 hours or even a day. The exponential distribution implies that over time, the chance of that happening is lower and lower. And this leads to a very special property of the exponential distribution called memorylessness. And what the memoryless property states is that future wait times are independent of previous wait times. So for example, if we've already waited 30 minutes between claims and we wanted to calculate the probability that we need to wait another 20 minutes, then that would be the same probability as if we hadn't waited at all and had to wait 20 minutes. And this property can be explained with a mathematical formula using conditional probability. If you want some practice, check out the link in the description below. The formulas for the PDF, the CDF, and the other properties for the exponential distribution are pretty easy to memorize. On the is it easy scale, this gets a 1 out of 5, meaning that it's the most difficult relative to the other distributions. And again, part of that is because it's a continuous distribution, so that means you will need to know calculus to solve questions involving the exponential distribution. Similar to the continuous uniform distribution, you may also get questions on deductibles and policy limits, so that also adds a layer of complexity. Will it be tested? This distribution is very likely to be tested, so it gets a 5 out of 5. The normal distribution is one of the most common, if not the most common, probability distribution. And because it's so different from the other distributions, we'll have a separate video on the intricacies of the normal distribution. The normal distribution is also known as the Gaussian distribution or a bell curve, because that's the shape that the PDF takes on. The normal distribution is so versatile mainly because of the central limit theorem, which we'll cover in more detail in a later video once we get to multivariate random variables. The basic premise of the central limit theorem is that even if your underlying data doesn't follow a normal distribution, with enough observations, the average of that data will follow a normal distribution. And that's really powerful because your observations aren't confined to any specific distribution. And so once you standardize it to a normal distribution, then you can calculate different statistics and draw observations on that data. The normal distribution has two parameters, u, which represents the mean, and sigma, which represents the standard deviation. So that's really convenient. The formula for the PDF is sort of messy, and I wouldn't prioritize memorizing this formula for the exam because you're really going to have to use this formula in calculations. When working with normal distributions, you'll be provided a standard normal table that you can use to look up certain values, and we'll talk about that in another video. Is it easy? This one also gets a 1 out of 5, meaning that relative to the other distributions, it's also one of the most difficult. The main reason is not because there's going to be calculus involved. More likely than not, you're not going to have to use calculus for normal distribution questions. You'll most likely have to convert a normal distribution into a standard normal distribution, which we'll talk about in another video. You can get questions on the central limit theorem, you can get questions on continuity corrections, and all these different properties around the normal distribution. And that's why it's one of the more difficult topics on the exam. Will it be tested? Yes. There are just so many questions the exam can ask on it, so this gets a 5 out of 5. Here are the questions for the continuous uniform, the exponential, and the normal distributions. All of the topics and questions are organized on the Actuarial Nexus, so if you're serious about passing the exam, be sure to check that out in the description below. Thanks for watching. In the next video, we'll close out this section with policy limits and deductibles.